Right, so thank you. First of all, I just want to say this is about the work that I did at Purdue during my postdoc. Even though right now I'm with ACI, I just want to make sure to say that these are my opinions and not the opinions of ACI. So today we're talking about the influence of cellulose nanofibers and limestone filler on the early age properties of 3D printing. So I think a lot of the challenges with 3D printing have been covered, but I just want to briefly talk about them. One of them is obviously the demanding rheological properties. Hopefully if this video plays, we know that we have to be able to pump the material, place it, and then we need to build up. And we typically want to have a very fast build-up so that we can take advantage of this technology. But a lot of times what we end up with is some failures. So this is what happened to the print that you're seeing here, is that we had a static yield failure at the bottom that caused the collapse of the material. And obviously, if you have a fast system, it means that this material is now going to waste. The other part, which this is part of, is the high carbon footprint and cost of these materials. We're seeing that the mix design is getting more complex. We're requiring more binders. And so we're seeing a much more higher carbon footprint than we would like to see with this technology. Still, we don't have complete answers on the durability and the durability performance, especially when we have things like cold joints or excessive shrinkage with the material. And this by itself feeds back into the high carbon footprint of the material. And lastly, we're still trying to find good strategies for reinforcement. So talking a little bit more deeper about the carbon emissions and the carbon footprint, what we're seeing over time is this increase in binder content. Even though we're trying to replace some of that cement with supplementary cementitious materials, we're still having mixed designs that have a much higher binder content, and that is mainly right now attributed to abandoning coarse aggregate. So we're seeing the use of fine aggregate and binder and relying on that, and that's leading to a lot of discussions on really how much of a concrete we're dealing with right now. The other things that we're seeing is we are putting a lot more admixtures into our systems, and even though sometimes these admixtures are at low content, they have a much higher carbon footprint. So if we look at the numbers of the carbon emissions of conventional concrete compared to 3D printed concrete, we would see that even if we replace half the cement with some supplementary cementitious materials, we are typically around the highest limit that we would see with conventional concrete in terms of carbon footprint. So conventional concrete would have a carbon footprint between 200 to 350 kilogram of CO2 equivalent per cubic meters. And 3D printed concrete right now, with a lot of the literature being between 350 to 600 kilograms of CO2 equivalent per cubic meters. And the other part that deals with this are the processes. So right now we're assuming that a lot of the processes that come with 3D printing are carbon neutral, but that's not really the reality of stuff, especially as this technology is developing. So as we are seeing this increase in productivity with this technology, we're seeing that the cement content, the carbon footprint, and the material cost are all going up as well. And we really, for this technology to progress and deliver its promises, we really have to reverse these. So if we look at the rheology and specifically the rheological admixtures used for 3D printing, a lot of the work done in this area was done early on for self-compacting concrete because we wanted to have very high fluidity. And when we went to that direction, we wanted to maintain high viscosity because that would help protect against segregation. So we saw that a lot of the admixtures is what you see in red dots over there. These are the typical admixtures that were developed for SCC, and so 3D printing really does not like high viscosity because it increases a lot of the demand for pumping. And so we really want to be where the black dots are. We want to have moderately low viscosity, and then we decide to deal with the dynamic yield stress afterwards. The complex thing about rheology is these properties are often linked together, so we really cannot pick and choose which property we increase and decrease, at least not easily or cheaply. So typically when we see an increase in static yield stress, we would see an increase in viscosity or at least increase in dynamic yield stress. And this is why we decided to look at a nano additive, so cellulose nanofibers. For those of you who don't know, we all know that most of the tree is actually made of wood, and at cross sections of the wood we see the growth rings, and those are composed of densely packed cells. And looking at the cell wall structures, this is where we would find the composite made of cellulose, hemicellulose, and lignin. And if we can mechanically and chemically exfoliate these, we would get our cellulose nanofibers. So in general, cellulose is the most abundant organic polymer in the world, and it's estimated to be between 100 and 150 billion tons of the biomass production around the world. So it's a pretty much an abundant organic polymer, and cellulose nanofibers more specifically are globally produced at large scale, so they are produced between 1,000 to 2,000 tons per year annually. And these are statistics from 2009 to 2013, so we expect that these got much higher. There were some studies on CNF in cement. We are not the first study to do this. And the early studies that did this looked at enhanced effects of hydration just by the fibril nature of CNF, but also found that there are increased material properties. So this is where we believe that there's interest in pursuing this, and we really wanted to see how is the rheology affected by this material. And because the CNF are an organic polymer, it makes them low carbon and a low cost material. So for this study, what we did is we wanted to increase the sustainability, so we wanted to also tackle that binder content. So one, we started with a PLC system, and our PLC system had 11% limestone content, and we looked at increasing that content to be 25 and 40. So because we had an initial 11% in the system, then we were replacing cement so that we have an additional 14% limestone or 29% limestone, leading to the totals that you see. Now, the limestone filler that we chose had a 1.4 micron average diameter particle sizing, so it's a much finer limestone filler, which would help us with packing density. The cellulose nanofibers that we used were obtained from University of Maine, and they were given to us in the gel form that you see in the left side, and this is what it would look like, this jelly-like material. This is at 3%. We diluted that 3% in water and obtained dosages of 0.15, 0.3, and briefly I'll share some slides when we also went to 0.5, but we really did not find that the 0.5 was workable. And here I just want to say those are mass additions of the binder. So we're looking at very low contents and seeing if those low contents can be effective. So the first thing that we did is we looked at isothermal calorimetry because we wanted to make sure that the system, at least in hydration, is behaving well. What you see on the left-hand side is the heat flow, and on the right-hand slide, we have the total heat. And here we're normalizing with the amount of cement in the mixture because this is the only hydrating part of our binder. And as you can see here, for the black line, you would see there's like some dotted lines around each of these lines. The dotted lines those are the mixes with CNF content, where when the color is changing, so from black to green to red, this is changing the content of limestone filler. So what we really found is that CNF is not significantly changing hydration, at least not at the quantities we're looking at. But we're seeing that with the addition of the limestone filler, we're seeing somewhat of an acceleration effect. So we're seeing the curves sort of jump to the left, and we're seeing an increase in heat of hydration. And this is not because the limestone filler is hydrating, but because it's giving us a lot of particle packing density that's helping with our system. So we wanted to probe that very early part of the hydration, and the best way to do this is by doing rheology. So we decided on this rheological protocol because it would allow us to, one, determine the rheology for 3D printing, but also it would let us sort of probe of what's happening at the early hydration. And so this is sort of the schematic of what we did. We started with a hysteresis loop, and by that we extracted the static yield stress. We modeled the downward curve with a Bingham model to get the dynamic viscosity and the dynamic yield stress. And then with the storage modulus, we were able to get it through some South measurements. So here are the results for the hysteresis loop. What you see on the left-hand side is the PLC system with different CNF dosages, but no additional limestone filler. And on the right-hand side, this is when we added 29% more limestone filler. And what you see, at least on the left, is that as we're adding CNF, we are significantly gaining structuration. So we're seeing an increase in the rate of thixotropy with the mixes. When we add the limestone, we see that the effect of CNF on the PLC limestone mixes are actually diminished. So we're seeing less increase in rate of structuration with the CNF. And if you compare the two gray lines between the two figures, which is comparing the PLC system to the PLC with limestone, we also do not see significant effect of adding the limestone filler to structuration. The second thing which we can take from this graph, so if we look at the peaks of these graphs, we can get the static yield stress. So first thing is just comparing the PLC system to the PLC with high limestone filler content. We see a significant increase in the static yield stress. But what we found that very critically is when we add CNF to the system, we have an increase in static yield stress, and that increase more or less is independent on the limestone filler content. So we're able to gain significant amount of static yield stress with very low dosages of CNF, and that is independent in a way of how much cement we had in the system, at least for the range that we looked. So with just incorporating limestone filler, we were able to gain 650% increase in static yield stress. And I'll dive a little bit more deeper about the data we got for the mix with CNF, but overall the maximum we reached was 1200%, which is very significant for such a low content of binder. The other thing, which is the interplay between viscosity and static yield stress. Having such increase in static yield stress is not very useful for 3D printing if viscosity is going at the same rate. So when we look at, let me control my animation. So when we look at the system with viscosity, in red is where you have the system in CNF without additional limestone, and we see that we are gaining the static yield stress, but we are also significantly gaining viscosity in that system. So that means that system, even though it can stiffen, it's still going to be very viscous, and so we're going to have challenges in pumping and extruding. But when we add the limestone filler system, even though it increases hydration or causes an acceleration effect, we're seeing the viscosity is actually not increasing as rapidly. So with that system, because we're sort of changing the hydration kinetics in that system, and we're sort of diluting the cement in a sense because we're keeping that water to binder ratio constant, we're able to have that increase in static yield stress without significant increase in viscosity. The other part, for those of you who are rheologically interested in the system, is looking at what's happening, at least in terms of storage modulus and the critical strain. So what you see for the mixes when we have the PLC, so again the blue dots, for storage modulus, we really don't see significant increase in storage modulus in the PLC system alone. So in a sense, this agrees with what we were seeing in the calorimetry. But what we're seeing with the PLC limestone system is we're seeing somewhat of a decrease with the storage modulus with adding more CNF. So those are the red squares up top. So by adding more CNF, we are decreasing the storage modulus. But what's interesting, because we're adding this nanofibers into the system, we're seeing that the critical strain is increasing. So in this sort of increasing morphology and aspect ratio of cellulose nanofibers, what we see is the storage modulus comes down, but the critical strain goes significantly higher. And if we look at the critical strain for a typical cement system, we know that the values that you see at the 0 CNF, this is around the limit for the critical strain for cement. So all the critical strain values that we're seeing post that are caused by the CNF themselves and not the cement. So if we take all the rheological properties and start translating them into printing, we can see how the printing system acts. So this is first on the small scale. So those are mortars, so those have very fine sand particles inside them. And we're seeing that for the first mix, so when we don't have anything, very early on, the print is going to start failing. In this case, we're trying to challenge the print and going in this rotating structure so that we can also look at the effects on the elastic modulus and buckling. So very early on, you see that this print is not going very well. When we look at only adding limestone fillers, so if we try to only rely on increased packing density, again, we see that the print is going to start buckling. Hopefully it will be clear. So this is where you see that top wall starts to buckle inwards. And that is mainly due to having low elastic modulus of our print. And lastly, when we go with the mixture where we have the high static yield stress, so high limestone filler content with 0.3% CNF, this is where we were able to obtain really good printing performance, which meant that we needed to add both parts of the system so that we can have this good printing performance. Now again, just trying to understand what's happening rheologically, we sort of can simplify things and look at the two main properties. So we can look at the static yield stress and the storage modulus and the effect of CNF in that system. And what we very early can see is the static yield stress is going up, but the storage modulus is going down. If we look at the origins of what rheological properties affect those, we would see that at least soft colloidal interactions are the one leading the interactions in the system and not the rigid interactions. So we know that the effects that we're seeing rheologically are more physical and less so being chemical. So we wanted to take this and do a large-scale evaluation, and we wanted to compare this to what's out there in industry. So we obtained some commercial material and again tried to do a challenging rotating structure, and here you can see around 8 layers we started to have some buckling issues in the system. Again, there's nothing wrong with this system, it's just trying to challenge the printing geometries and seeing the limits of the rheology of the system. And here it's important for me to say, so when we use the same mixture for other geometries, it performs completely normal. For our system, we were able to push the envelope and go to much higher layers. We were able to get failure around 73. And again, if you're working in this technology, this is kind of the fun part of just printing stuff so that they can fail. So knowing where the buildability was, we were able to go back and just have something that stops before that. We also wanted to make sure that if we're doing this, we're not sacrificing mechanical properties. And so we measured the compressive strength and flexure strength. The compressive strength was measured with cast specimens, whereas the flexural strength was measured with printed specimens. And the main reason for doing this is because we know there is some fiber alignment effects that happens with 3D printing, and so we wanted to see if this would translate to nanofibers as well. And what we see here, there are some increases that we see in the compressive strength system, so this aligns to what the literature says, but at least for flexure, we did not see significant increase in the flexure. So we did not really anticipate some fiber alignment that happens with 3D printing like we see with microfibers. And the last thing is we wanted to see if there are some effects on hydration of the system. And this is why we did some TGA measurements to try and capture the chemically bound water in the system. And what you see here is, for the most part, those lines stay more or less horizontal or within the statistical error of our measurements. So we did not really find a lot of effects on chemically bound water or hydration for the CNF, at least in the contents that we're looking at. So the last thing to talk about here is the cost of this and the effectiveness of it. So we sort of wanted to normalize our study and look at how much do you need in rheological additives to achieve twice the static yield stress. So looking at 100% increase in static yield stress. What you see here is with CNFs, we're able to achieve that at almost 0.04% of the weight of binder. And this translates to a cost of 0.92 US dollars, not Canadian dollars. And comparing this to other rheological additives, so something like nanoclays, which we know are very effective, we actually are much lower than that. Same thing with other polymers. So if we look at cellulose ethers as a polymer, we cannot get the same performance. And again, comparing it to silica fume or nanosilica, those perform at a much higher cost and a much higher content. And this leads us to what carbon effect this has on our system. So because we're able to achieve such high rheological performance with such low doses using an organic polymer that is abundantly available in the industry, we can get total carbon emissions that fall just under conventional regular concrete. So we're able to be below the 100 kilogram of equivalent carbon dioxide per meter cube with our mix design. And this is significantly lower than a lot of current 3D printing materials mixes that are out there. So to sort of just summarize, so we were able to see that we have a significant increase in static yield stress. There were some increases in compressive strength, roughly by 20%, but there were not really significant effects on flexure. And we saw that there are some synergetic effects, and we were able to sort of determine that where these interactions are coming from in the system, and that we need both the CNF and the limestone filler. And it does not have to be exactly limestone filler, but it can be other fillers as well, because those interactions are physical and not chemical. And last thing is we were able to get really high performance with printing. So the future work, not for me, but for other people at Purdue, are to just optimize the mix design to have a much lower carbon footprint of this mix design, and to sort of evaluate the cellulose nanofibers and the durability. And with that, I'm happy to take more questions.